Hello, welcome to another lesson. So today we're going to tackle the topic of transformation of functions, which is a new topic to the new syllabus of for advanced maths. I say it's new for New South Wales. So this topic has been seen in various parts of Australia before, so especially in Victoria. So what we're going to do this in three parts. So for the first lesson, I'm going to basically set a framework for the different types of transformations of functions. The next lesson, we're going to basically do a few more questions and maybe apply transformations specifically to trig functions. And then for the last lesson, maybe explore a few questions that are seen in past papers. Now, there's not a lot of past papers in New South Wales that have this concept really explored. So I'm going to tackle some questions from the Victorian past papers. So that's the plan. So without further ado, let's hit up the slides, and here we go. So I want to set forward a framework for doing this. So now, for those that have been in my classes, we had, transformation of functions is not new. Transformation of functions has always been done. It just goes by different names at different times. So I'm going to ambitiously try to capture all the transformations, of functions, maybe give it a bit of heading there. I'm going to ambitiously try to capture all the transformations of functions all in the one diagram, and then I'll start talking about this concept of commute or not commute, which basically means the order matters or doesn't. And then basically give you some general rules before we do some questions. So what I'm going to do ambitiously in this diagram, I'm going to, in the middle here, maybe I'll zoom in to give it a bit more neatness. I'm going to have a function, and this function is going to look like that. Let's say, for ease of understanding, call this function y equals fx. So if we have some sort of generic function that looks like that, what I'm going to do ambitiously is that I'm going to manipulate this function in 6 ways, which represents the 3 common types of transformations that we apply in this topic. So the 3 types of transformations we'll see in this topic is reflection, which, like I said, this isn't a new concept. So prior to the new syllabus calling it reflection, I used to just call this flipping. So my classes would just use the term flipping, so flips on the y, flips on the x, and then you have this concept of dilation, which some schools call it stretch or compression, but that for me was steepness. And then last but not least, they have translation, which for my class, we used to just call it shifting. So shifting up, down, left, right, etc. So these 3 concepts are not new. They're just termed differently. So what I'm going to do for this particular function now, I'll just see if I can shrink. Yep, perfect. I can actually shrink that, which is good. Right now it's a bit too big. Yep, that's fine. All right. So what I'm going to do is I'm going to put this guy in the middle and then have sort of 6 arrows come out of it. So maybe for the first 2 upstairs, we'll explore reflection, which is not a hard concept. So if I had y equals to negative of fx, that basically reflects the function about the x-axis. So this one here, let's give it a heading right on top, reflection about x-axis. So then my function, it's having the green line there as a mirror, would basically just go down there. Now I won't label everything just to, in the interest of speed. So reflection about the x-axis is the first one. Next one, logically, we would then reflect it about the y, whereby I would put the negative inside in front of x. Now, technically speaking, to really understand this, the easy concept is that if you want to reflect about the x-axis, you put the negative in front of here, right? And then when you bring that negative over, it goes in front of the fx. And then when you want a reflection, when you have a reflection about y-axis, you put the negative in front of x, and that makes sense. So that's how you sort of remember. So this one here, the mirror is on the y-axis. So if you take this original here, we would then go backwards of some sort. Sorry, my teacher's pen isn't as neat. Yep. So that in itself is not rocket science. We've done that before in the old syllabus. The new syllabus just calls it by a different name, reflection. Yep. So that hopefully wasn't too bad. Let me just move this so it's a bit more centered. So then the next two. Let's deal with dilation. Now, dilation in itself isn't hard. It's steepness and, well, compression to an extent. So what I used to say to my class was, if we had a number in front, let's say this number was a, and I was multiplying by the function, that it causes the graph to basically get stretched or is a bit steeper. Now, if you think about that a, technically, once again, it used to be on the a over here. So from an algebra point of view, you basically divide by a, and then you multiply it up to get the a on the right-hand side. So when you multiply that, let me just name it first. So this is a vertical dilation. Yeah, where, just to be clear, this factor of a is the dilation factor, they call it. So whenever you hear that a function is dilated by a factor of 2, that's where the 2 goes, or dilation of factor of a half, that's where it goes. And it sort of makes sense that if you're dilating a function vertically by a factor of 2, it stretches it, it doubles the height by 2. Now to illustrate that, here is, if the height here goes down to, sorry, that should be a -2. If it goes down to -2, then theoretically, if I dilate it by a factor of 2, it'll cause it to go further down. So -2 is over here, and because this is a, I don't really know what that is, but 2 times a factor of a, assuming in this case that a is bigger than 1. So basically, if a is bigger than 1, it'll cause it to stretch. So some schools use the term stretch, but when it's less than 1, let's say a fraction of a half, they say compression. So if there's a compression of by a factor of half, you multiply by half. So that's vertical dilation. And then by the same token, if I want horizontal dilation, I basically would put the a factor, and remember I said to you, and this is really important for algebra purposes, technically speaking, that a is divided. So if you want vertical dilation, you divide y by a to get the a up here. Which basically means if I want horizontal dilation, I would divide the a inside to where x is to get the effect of stretching and compressing on the x. Now, if you think about it, if a is a number that's big, it'll basically stretch on the vertical, it'll stretch it upwards. And if a on the horizontal was big, it'll stretch on the horizontal axis. So by dividing by a, in this case, and I want to see if I can fit it good. This guy has an effect right now. If the original was at 2, then you would expect, now I haven't made it lower, so it's still a -2, but you would expect 2 to be there, and that factor there to be something that's bigger than 2 in that case. So it might be 2a as a root. So horizontal, vertical basically stretches it up and down. Horizontal basically stretches it left and right. So it's not a new concept. It is a new terminology that they threw into the syllabus, dilation, which used to basically be called steepness. So the last two, once again, not too hard. In fact, it's probably the easiest one to, aside from reflection maybe, and it's pretty straightforward to understand. So we have vertical translation, and horizontal translation as well. So we know that vertical translation, we basically take whatever function we have and we add a factor or add a component outside of it. And similarly, if I have horizontal translation, I have the additional subtraction inside the function. Now, for this one here, I did plus a because when you plus a, it shifts or translates the function in a positive direction. So it might be such that the a would throw it. So it used to be at the origin, but now it's at a. And similarly, for the horizontal piece, if it used to be at their origin there, by minusing it, I might have shifted it over by a units over here, and this might be 2 plus a units. So I guess what I'm trying to say is this terminology is new, yes, translation, dilation, and reflection, but the concept itself is not. So they're the 6 key transformations that can occur. It's a really neat diagram to summarize all of them. So what I also want to talk about now is this concept of commutation, or whether something commutes. So commute is transformations that commute is defined as the following. So let me just write a title. So transformations. So maybe it's worthwhile highlighting the 3 cases that do commute and the 2 cases that don't. But before I do that, obviously, maybe this concept of commute should be defined. And commute is quite simply the order in which the transformations occur do not matter. I'll underline that because that's the key word there, right? So what this means is that I'll sort of put a little box around this as definition. So if I basically have 2 functions, or sorry, 2 transformations, if the order in which I do them don't matter, then it's said that these transformations commute. On the flip side, if the order of which I do the transformations impact the final result, in other words, if I do one and then the other, and then swap it around and it gives me a different function and a different graph, then it says that the 2 transformations do not commute. So ones that commute. So, I mean, these ones here are pretty, I mean, there's only 3 cases here. So if I have 2 translations, one vertical and one horizontal, it doesn't matter which one I do first. So in old syllabus speak, if I'm shifting something to the right and then shifting something down, it doesn't matter whether I go to the right, down in that order, or down and then right, the graph is the same. So 2 translations, absolutely fine. 2 dilations, absolutely fine. Right, so if I basically compress one and compress the other, the order doesn't matter. Now the next one is interesting. So one translation in a direction plus one dilation in the other, and this is key. So if you had one translation horizontally and one dilation vertically, doesn't matter which order you do. However, in the case where there's one translation horizontally and one dilation horizontally, the order does matter and it does impact it, and it gives us a nice little list for the ones that do not commute. So the opposite to this one, when you have one translation plus one dilation in same direction. And any reflection and translations do not commute. So they're the cases we're going to explore. And I guess a useful thing once you have this is, what if I gave you a formula that had everything in there, just like how I gave you that diagram that had all the 6 options. If I gave you a formula that had everything in there and then give you almost like a pecking order for you to go through, that might be useful. So let's explore this sort of all-in-one formula. So part 3. And once we do this, we'll do some questions that basically explore some of these transformations. So maybe I'll go and combining all transformations. I think this is useful. I think this is useful because it shows you what you should, how would you would describe some of the transformations in a certain order. In the order that you should, right? So, for example, this is ambitious. So, if I said to you, I had y equals to fx as my original function, right? That is the original function, and I want to transform this by reflecting, dilating, and translating, then this is how the formula would look. Now, I'll put everything in there, so it's going to look a little bit convoluted, but hopefully it's useful for you to see. It's like a formula that captures everything. So if I said plus minus, I'll put a k there because that's a very common constant to use for vertical dilation. Now, the plus minus there, for those that are on top of their game, you know that that represents reflection about the x-axis, so vertical reflection. Then I have the function there, and this is where I'll put everything in here. So there's another plus minus here, and for those that know, if it's plus minus inside the function, that is horizontal or reflection about the y-axis. And then I'm going to put 1 on a in front of x minus b, and then at the end there, plus c. All right. Wow, it's got a lot in there, and we're going to unpick all 6 transformations as it relates to the formula. So we've explored all 6 in that mind map of a diagram. Now we're going to explore all 6 within a formula setting, right? So I'm just going to highlight this because I'm going to now unpick it all. Let me just circle the ones first for reflection. So this one here represents reflection about x-axis, right? So sometimes they call it vertical reflection. This one here, by the same token, is reflection about y-axis. And when it comes to a pecking order, we always do reflection first. Second one, let's unpick our dilation factors. So we got 2 dilations here. This guy here, if you think about it, that k could have been like over here divided by k, which then gives the sense that x on a, yep, and x on a and y on k. So that one there is the vertical dilation of factor k. And this one here, by the same token, will be horizontal dilation by, of factor A. And let me just grab a different colored pen here. And then last but not least, we have that and this. So this one here is a horizontal translation Now, I did it on purpose where it's a minus and a plus, so I can say the words translation of, I'll say, to the right. Otherwise, I have to say left and right. But let's be specific. If that was a minus, to the right of B, right? So B units to the right. And this one here, vertical translation. Now, if it's plus C, it'll be upwards of C. So that captures all 6 transformations at the same time. Now, if we were to give this an order, right? So maybe I'll put point 4 here, order for transformation. So in the questions that basically give you an original function and then an equation for a transformed function, and they say, describe the transformations that go from A to B. This is the order that you might want to consider, right? So the first one is reflections. Yep, go there. So the 2 black circled equation parts upstairs, reflections is number 1. And then you have a choice. You either go vertical or horizontal. Remember, the order for horizontal and vertical doesn't matter. I'd always go vertical if I had to choose. And always go dilation before translation. But never go vertical dilation, horizontal dilation, vertical translation. Go vertical with verticals, and then horizontal horizontals. Yep, horizontal horizontals. And it's always dilation before translation. And that is a good pecking order for us to work down in terms of our order for consideration. So I'm just going to put a box around that. So that's the theory for transformation. Let's do 2 or 3 questions just to bring this to life, and we'll end the video there. Next lesson, we'll do a few more questions and maybe explore this under trigonometry, trig functions. And then the last lesson, I'm hoping to do a few past paper questions amongst other things as well. So I've actually prepared a question in advance. Let me see if I can find it. There it is. So this is, I guess, a classic question for you to get under the new syllabus. So we have a function, right, that's been given, and it's a hyperbola. And undergoes the following transformations. Let's see. Reflection about the x, vertical translation of 4 units down, horizontal dilation by a factor of 3. Find the equation. So there's 2 parts to this question. Find the equation and sketch, right? Piece of cake. So let's explore these, right? So I have a function, y equals to 1 on x. Let's do this each in turn, right? So the first thing that I do is that there's a reflection about the x-axis. Now I know what that means is it's going to come downstairs, which means from a formula point of view, and maybe for each step of a change, I'll use a green pen to illustrate the new component. And maybe I'll slowly tick it off. So reflection about the x-axis, that's a negative there, tick. Right, formula-wise, just a negative in front, and it will flip it downstairs, right? See, I keep using the old language, flipping it downstairs. So reflecting about the x-axis, same thing. Next one, vertical translate. So shift down by 4 units. So we know that we already now have the negative 1 on x, and we want to shift this guy down by 4, or vertically translate downwards by 4. That's a -4 outside of the function. And last but not least, it wants a horizontal dilation, right? By fact, what that means graphically, horizontal dilation by factor of 3 means to horizontally stretch it by 3. Now, horizontally stretching something by 3 looks like it's making it shallower, right? So basically what that means is any equation with a dilation horizontally will look like this. You basically replace whatever you have in the x, replace it with x on a, whatever that factor is, right? So in this case, the a is 3. So formula-wise, so let me just copy everything down. So I've got the -4 in here. And the new part here for the third component, so I've done that one. For this one, you basically x on 3 on that. Right? So if I clean up for the final answer, therefore the 3 comes upstairs, y equals to minus 3 on x minus 4 would be my final transformed function. Right? Not too hard. Just the language gets a bit of getting used to, right? And then if I was to do a rough sketch on this, right? This one here is a hyperbola that has been translated, I was going to say shift, down by 4. And that negative, should have started with that. Negative meant that instead of in the first and third quadrants, second and the fourth, down by 4, and then horizontally dilated. So that 3 basically magnifies the horizontal by 3, which has the effect of basically for a hyperbola just shifting outwards. So the best way to capture, sorry, let me go closer to the asymptote. The best way to capture dilation is by subbing in a point. It's a very smart thing to do. Maybe when x equals to 1, what's that? Minus 3, minus 4, minus 7 would be a good way of capturing the dilation. So that would be y equals to minus 3 on x minus 7, so minus 4 rather, and then origin x and y. So nothing too fancy about that question, but new syllabus terminology is in play there. Hopefully that was okay. Let's do another one. So here we have another question, and this one here is a parabola that's factorized. I like this one because there's 2 values of x, which when I horizontally dilate it, it goes for a bit more of an interesting equation. So what's my 3 transformations? Is reflection about the x, same thing, vertical dilation, and then horizontal dilation. Oh, perfect. What am I doing? The same thing, so equation and sketch. Perfect. All right, let's do this again. So I start off with my untransformed function. And then the first thing I'm going to do, reflect this about the x. So basically flip it downstairs in the old language that I would use in my class. So I would copy the function as is, and to flip this downstairs, put a negative in front, right? That takes care of the first reflection transformation. So second one. So vertical dilation. Now there's 2 ways to do this, right? You can do it in 1 or 2 steps. So if I have a negative there, so you can put in the half downstairs, because that's whenever you go vertical dilation, that's technically where it goes, but you always then multiply it up. So why don't we skip the middleman and put the half there, right? And that would vertically dilate by a factor. What that means is it compresses, right? So if that was a half, compresses. If that was like 5, stretch. Yeah, pretty easy. So that is vertical dilation. Now the third one is, not as straightforward as a lot of people put it. So I want this to horizontally dilate by a factor of 3. This is what I do. So negative half is there now. So there's a +1 and a -3. So when you dilate horizontally in the algebra, in the equation, what you do is for every time you see x, you replace by x on whatever factor you're dilating by, in this case 3, x on 3, x on 3. Yeah, so if it was a dilation factor of a half, it'd be x on half, easy. And that technically is your equation. Now, we're just going to clean this up to get the final answer. So we're pretty much done. So what I'm going to do is common denominator each individual bracket. And interestingly, right, and you will see this in textbooks, when you horizontally dilate like this, you're going to get different roots, right? Because the original roots, the initial x-intercept was -1 and 3. When you sort of stretch it, your roots change, right? And that makes absolute sense. So you can see here, the reason why I'm drawing that out, when you common denominator this, look at the 2 brackets. So if I take out all the whole numbers downstairs and combine it with a half out front, I get, therefore, y equals, actually, maybe I won't, wait, do it again. Therefore, y equals to, so 2 times 3, that's 18. But the 2 brackets is x plus 3 and x minus 9, which makes sense, right? Because if I have a parabola that cuts it at 2 points right now, if I stretch this parabola horizontally, it'll cut at 2 separate points, right? That's exactly what that concept is trying to illustrate. So that's my equation after I've translated. So keep in mind, right, that when you horizontally dilate, you're going to change your x-intercept, right? And that's perfectly normal. And now, just to illustrate this, right? So in green, I'll just quickly draw the original, which used to be at -1 and 3, right? So some sort of parabola looks like, but this guy here doesn't just flip it upside down, which is reflection about the x, and it doesn't just stretch it vertically. It then pulls it wide and gives us an upside down parabola, or as I like to call it, a sad face, and 3 and 9, sort of something that looks bigly like. Missed that a bit, make it a bit bigger. Yes. Yep. So something that looks like that is the net result of all your transformations. So hopefully that makes sense. And I think, like, I can't emphasize this enough. See that 3 there? That's 9 now. See that 1 there? -1? That's -3 now. It's made it wider because I've horizontally stretched up, horizontally dilated it, right? That's interesting. That's interesting. Changes the roots. So just to clean up my labeling, that's X, that's origin, that's Y, and that's done. Was that okay? So you don't need the green. The green is basically to illustrate what the original graph looked like. After 3 separate transformations, you get the black. Is that, oh, sorry, there is an 18 here. Is that okay? So let's do one more question, right? And I think that should do us for the first lesson. So in the next one, we're going to go a bit backwards, where instead of me giving you verbally in words the transformations, I'm going to give you the equations, and then the question asks for you to list down the sequence of transformations that you do. Remember, if it doesn't tell you, and it doesn't tell you, the pecking order that we should follow is reflections, verticals, and horizontals. And within verticals, it's dilation and then translation. Yeah. So let's see what I'm saying here. So part A, I want to move the root x function. Right, that's my original. I want to move that to y equals to 4 root x minus 1. Right? So within the transform function, and it's worthwhile highlighting this, that multiplying by 4, which could be downstairs here, is a vertical dilation. And this -1 inside the function is a horizontal translation. Yeah, see how it's -1, so it's translating to the right. So our answer then would be to describe both of these now. For this one, remember I said to you, dilation and translation, it doesn't matter if it's one of each across vertical and horizontal. It doesn't matter which order they commute, so it doesn't matter which one you put first. But as a rule of thumb, do the verticals first. So this one, the answer would be vertical dilation. Because it's 4, you can even use the word stretch, right? And then you go by factor of 4, and then horizontal. So if your school teacher doesn't like you shortening the word vertical and horizontal, don't. I'm lazy, so there it is. Translation now, give a direction, right? To the right by 1. That's my answer, right? Nothing too wow about that. Nothing too wow. Pretty straightforward, right? The order in this case doesn't matter, right? Because it commutes, and hopefully that makes sense. Let's do puppy. Puppy. Now, this one here is a bit more involved. Let's see what, oops, highlighter. Let's see what we have here. So we're going to move from a root x function to something a bit more complicated, where it's like 9 minus 2 root x plus 6. All right. There's a few things happening here. Let's unpick them. So, I mean, that is like a +9 outside. So this guy, firstly, is a vertical translation, right? And it's positive, so I'm shifting that up. There's a negative technically in front of the square root. So this is a reflection. And because it's a negative outside of the square root and not inside where the x is, it's going to be about x-axis. in other words, flipping downstairs. So just get in your mind, right? So if it's about the x-axis, it's flipping downstairs. If it's about the y-axis, flipping left and right. Yeah. There's a 2 in front, which we know old syllabus talk is steepness. New syllabus talk, vertical dilation. And then there's a +6 inside the function. Old school talk, shift 6 to the left, but this one's horizontal translation. So there's 4 transformations at play. Remember the order: reflection, your verticals with dilation before translation, and then horizontal. So once you sort of get that pecking order down your belt, it's pretty predictable, right? Reflection about x-axis, vertical dilation first. Yep. And remember, if it's dilation and translation, the order absolutely matters if it's both vertical, right? So dilation comes first, translation comes after, and you shouldn't go wrong. So vertical dilation by factor of 2, which makes it steeper, right? Or stretch even. Vertical translation. Now, 9 upwards by 9, and then horizontally translate to the left by 6, and that is your answer. So follow that pecking order and you should be fine. So we have 4 transformations there to get us from y equals root x to that function there. Hopefully that was good. So that was a bit of a framework for us to deal with transformations. I really like that diagram that puts all 6 of them together, and I really like that all-in-one formula that has all the equation bits for transformation. The order for you to do things, the pecking order, as I like to call it, is important, especially for tackling questions like this. Next week, we'll do a few more questions and then apply this to trig functions, and then to past paper questions in video 3. Thanks for that. I'll see you guys later.